compensation specifically. So if we have a system, let's say we have let's say that, for example, we have this system here where we use pure gaining type of compensation. And let the plant be 1 over S, S plus 1, S plus 2. And so we can draw the root locus for this as the gain K increases from 0 to infinity. And so, what we do is put down the pole, all the poles. We have a pole at -1 and another one at -2. And so we know the root locus will exist here, it will move in that direction, in that direction, in that direction, and it will break away somewhere. And, if you didn't have that pole there, it would just break away and go up and down, vertically up and down in the middle at -0.5. But with the pole will basically repel the root locus. Okay, and so in fact the breakaway point will be to the right of the middle, somewhere to the right of the middle, and it will go unstable eventually as the gain K increases. And so that's using pure gain compensation. But what if we wanted a pole? What if we'd like to have a pole over there? And in other words, a complex conjugate pole, one up here and its conjugate down here. There's no way to adjust the gain K from 0 to no value gain K from 0 to infinity will cause the root locus to go through there at that point, and its complex conjugate down there. So what we need to do is use something that will attract the root locus toward it. Okay, and just as we were saying, this pole, if you didn't have that pole, it repels it. If you didn't have that, it would be vertical in the middle. Right? If you put the pole there, it repels it. If you put a 0 there, it'll attract it. Okay, so we want to talk about first the lead compensator. And in general, this is GC of S. Just leave it as K. But in general, it's GC of S. And you see that when you're talking about a lead or lag compensator, the form of the lead or lag compensator is a constant S plus A over S plus B. And so lead, L-E-A-D, is such that the B is greater than A. Right? And lag is such that B is less than A. Okay, so, and so the next question is, where do we put these values of, well, the pole would be minus B and the 0 at minus A. Where do we put them so as to, such that the control system specifications are satisfied? Okay, and well, anyway, we have a 0. The 0 at S equals minus A, the pole at S equals minus B there. And so if B is greater than A for a lead compensator, then minus B is less than minus A for a lead compensator, right? And if this is true, this is also true, right? In inequality direction. the inequality, direction changes direction. Yeah. And so here, minus b will be greater than minus a. And so if you look at these in S plane, say, for the lead, then we have minus b is less than minus a, means that the pole will be to the left of the zero. Okay, minus b is less than. And over here for the lag compensator, we'll see that when we do the lag compensator design, that we're going to be placing the pole and zero close to the origin. And we'll talk about that, But so here it would be a zero and a pole. That would be for the lag compensator. So we have, this dividing line here. The lag.
Should A be a pole?
They should be here.
Should be here.
On the lead compensator.
On the S plane.
Oh, yeah. This is a zero. So the zero is to the right of the pole. For the lead compensator, and it's just the opposite for lag compensator. And also we talked about how to implement the lag or lead compensator. You can use the RC circuit. It was looking like this. We have an R, C here, followed by goes into the op amp minus plus, and this is ground, and up here we have another parallel R, C, and that then goes into a resistance, and that goes into the op amp minus plus, and another resistance here, and that's the S, and E and S, and this is R1, C1, R2, C2, R3, R4. Okay, and these two will be isolated from each other, right? This op amp circuit here will be isolated from that there because for an ideal op amp, you can say that they will be isolated, and so you can find the transfer function of this and multiply it by the transfer function of that. And remember the transfer function, if we call this Z1 and that Z2, in other words, the Z1 is this and the Z2 is that, then we could express E out over E in as minus, we had it in terms of Z2 over Z1, minus Z2 over Z1, that takes care of the first part. And then we have that times minus R4 over R3. And so the minuses cancel out. And this can also be expressed as minus Y1 over Y2 times, and I'll just throw away the minus signs now, R4 over R3, right? Y1 is a reciprocal of C1, and so in this particular case, the Y1 is the 1 over R1 plus SC1, and so we have that over 1 over R2 plus SC2, and then this is times R4 over R3, okay, and so you can factor out a C1 in the numerator and a C2 in the denominator. So what you'll end up with is R4 C1, R4 C1 divided by R3C2, and then we'll have S plus 1 over R1C1 divided by S plus 1 over R2C2. And so this here, you can call it the K sub C, and this A, and this B, right? So the A is 1 over R1C1, B 1 over R2C2, K sub C is this ratio here. And so if, what did we say, that B is less than A, B greater than A, so this greater than that. What that means, therefore, is that R1C1 will be greater than R2C2. Sorry, this is over R2C2. Yeah. R1C. Yeah. So, right. Okay. So, and that's for the lead. Right. And it's just the opposite for the lag. That's R1C1 less than R2C2 for the lag. So, this is the analog compensator. Right. These days it's not done with analog. It's done digitally. You can convert you can convert the this transfer function here. Once you know the values, you can convert this transfer function to a discrete time transfer function. And well, basically, this corresponds to a certain differential equation, and the differential equation can be approximated by a difference equation. Okay, and the difference equation can be programmed on the computer, and so that code can serve as the controller, our controller lead or lag compensator. Okay, so what we're going to talk about the effect of lead. The question is, why is it called lead compensator or lag compensator? If you have if you have a lead compensator and you apply a sinusoidal input to it, the output here will lead the input. In other words, if this is the input sinusoid, the output sinusoid would be shifted to the left. Like that, it's leading. Okay, that's for a lead compensator. A lag compensator would come lag, right? It would come after. Right, so this is the lead. So this is the red is the input, the blue is the output. Okay, and the lag compensator is just the opposite. Okay. You have the sinusoidal input, and the output will lag the input. In other words, the time difference at which they achieve their maximum. This one is advanced in time for the lead compensator. It's delayed in time for the lag compensator. Okay, so let's see. Yeah, so let's get into an example. And So as we were saying, or in the beginning, that with pure gain compensation, you may not be able to get the kind of response that you want, okay? In other words, the location of the poles can't be shifted if you're using pure gain compensation. And the purpose of the lead compensator is in fact to reshape the locus, okay? So let's say that we have this system here, control system. We have, with pure gain compensation, it's a simpler system than this one that I have right here. So it's a 10 over s plus 1. Okay. And pure gain compensation, and you have a pole at the origin, you have a pole at -1. And so the root locus would look like this. And the breakaway would occur at -0.5. Okay. Let's say that you would like closed loop transfer function pole such that the damping ratio zeta is equal to 0.5. So this is the spec damping ratio, and the undamped natural frequency is equal to 3 radians per second. All right, and so I could have instead of specifying zeta and omega n, could have specified something like the zeta and the settling time, because remember the settling time T sub s is equal to 4 over zeta omega n. So if you know the settling time and you know the damping ratio, then you can find the omega sub n. Okay, so there are different ways to present the specifications. So let's just say that the specifications are these here. Okay, and if these are the specifications, then you know that the desired closed loop transfer function pole will be, you can determine where it will be. Well, let's take a look at the characteristic equation of this system. It's going to be s squared plus s plus 10k. Or the characteristic polynomial, that's a characteristic polynomial. And over here, in general, you see it's going to be, in fact, the closed loop transfer function will be k over forward path gain divided 10k. Yeah, so that's the C of s over R of s. And that's the C of s and the R of s. Okay. And over here, the characteristic equation will be s squared plus 2 zeta omega n s plus omega n squared. Okay. And it equals 0, or this characteristic polynomial. And if you set it equal to 0 and find the roots will be minus zeta omega n plus and minus j times omega d. This is minus j omega d, and omega d is equal to omega n times the square root of 1 minus zeta squared. And that's omega sub n. And so you see we can determine where our desired closed loop transfer function poles are just using this zeta and omega n, right? And so they will be at minus zeta omega n, which is minus 1.5 plus and minus j times omega d. Omega d is equal to omega n, which is 3 times the square root of 1 minus zeta squared. And that's, this is 1 over 2. And this is equal to, minus 1.5 plus minus j. Whatever it is, 3 over square root 2. Okay, so that's it. These are the desired closed loop transfer function poles to satisfy that these two specifications here. Okay, and where are they? There, this is minus 1, this is minus 0.5, so minus 1.5 is right there, minus 1.5. And then you have j, 3 over square root 2, which is roughly 2, right? And so it's minus 1.5 plus and minus j2. And you see, with pure gain compensation, like here, there's no way to satisfy that specification because the real component will never be minus 1.5, right? So what we'll do is we'll use the lead compensator to attract that root locus. The 0 of the lead compensator will attract that root locus. So we can redraw it. Okay, so our control system now look like this. We have the compensator is the K sub C, S plus A over S plus B. And then we have the plant, which is 10 over S, S plus 1. Okay, and unity feedback. And so we would like to determine A and B in order to satisfy these two specifications. In other words, in order to be able to get the closed loop transfer function poles to be here. Okay, and so we can start drawing the root locus here. Just to give you an idea, we have the pole at the origin, the pole at minus 1. Okay, and then you see, if we had a 0 over here somewhere, what would the root locus look like? What would the root locus look like?
Yeah, they would converge and then split off, circle around that, and then go to negative infinity and the 0.
So,
needed the left side.
Mm-hmm.
so it would be a little bit to the left of the center now, because the 0 is attracting it.
Oh, okay.
And it'll be circle. Okay, moves this way and moves that way towards the pole at minus infinity, the 0 at minus infinity, where k equals infinity. So that is if you use a single, proportional plus derivative, right? It's as if you had only this here, okay? And this is minus a, okay? And so that would work. However, we want to use this form here, right? Lead compensator. This form here is proportional plus derivative, right? PD. Right? This form, and that is a lead compensator. Okay, but it has a 0 at a finite 0 and one pole at infinity, right? As a pole at infinity. We want to use this form here, and so we have to modify this consequently. In fact, instead of looking like this, we can redraw it. We have the pole at origin, pole at minus 1. So we have the 0 and the pole. Okay? So this is for the compensator here. Okay, and so the root locus exists here, it exists here, it moves that way, away from that, away from there, away from there. It's going to break away somewhere. Now, the question is, how many asymptotes do we have here? The difference between the numerator and denominator. Two. This is third order, that's first order, so two asymptotes. And therefore, the angles of the asymptotes are going to be what?
90.
Plus and minus 90, right? And then we also can find the origin. Oh, if we knew exactly what A and B were, okay, origin of the asymptote. But there'll be plus and minus 90. Let's say that there's somewhere that the asymptote, that the origin is somewhere here, right? And it would be somewhere in, there, because this 0 here is attracting the root locus, okay? And so it's going to break away. One branch is going to go up that way, and the other branch is going to go down that way. And so instead of having the cross, which if you take these away, you just have a cross which breaks away in the middle, you have this, which allows you to, you see the root locus has been reshaped, reshaped, and so if you remember, you couldn't, with pure gain compensation, you couldn't satisfy the real component minus 1.5. It was always going to be at minus 0.5, right? If you didn't have these, the breakaway would be minus 0.5 in the middle there. But now, with the lead compensator here, we've reshaped the root locus, and it's possible to basically get that closed loop transfer function pole to be further into the left half plane, right? At the minus 1.5, plus or minus.
Is that hoping that the asymptote falls a little bit to the left of -1.5?
Yeah, the asymptote would have to, at some point, maybe this point here, in fact, I should make it a little bit more exaggerated, right? Like this. If this is -1, this is -2, say, minus 1.5 would be right in there. So let's say that the asymptote is here and here. So it would go like that and like that. Okay. So it has a chance of hitting that real component. Okay. So what we have to do is determine the location of the 0 and the pole, such that we satisfy that specification there, okay? And what you can see here is that there are several possible solutions to this problem, right? Maybe if we move this one over there and move this one this way a little bit, you would still be able to, satisfy for a certain value of the gain k, or k sub c, I should say, for a certain value of the gain k sub c, satisfy the specifications. Basically, the specifications result in these closed loop transfer function poles. So there are an infinite number of solutions to this problem. The book takes a look at 2. Okay. And the first one is called, actually it's the second one. It's called pole 0 cancellation.
So would the left one work then also?
Sorry?
Would the left one work then also? Could that be a possible solution? Is that what you're saying?
This it could be a possible solution, but this is more general up here. Okay. Let's consider, before we look specifically at pole 0 cancellation, let's take a look at this particular problem with these particular specifications. Let me redraw this, and I'm not going to put in the root locus plot just yet. So, we have the pole to origin, pole minus 1. We have minus A and minus B, and pole to 0. And then we have the desired closed loop transfer function pole. And we'll look at one of them, right? This is minus 1, and minus 1.5 is roughly here, say. We don't know where these two are yet, okay? But let's say that this is actually it would be a little bit right here, right? That distance there, that distance there. And so minus 1.5 and J 2.6. 2.59. Okay. J 2.6 roughly. And so that is our desired pole. We want to draw a vector from each of the poles and zeros to that desired point there. And you see what I'm getting at is the angle condition, right? When you draw a vector from each of the poles. And okay, so we have this one here, and we'll call that angle there theta sub p. And then we have this angle here, theta sub z. Okay, and that's at minus a. And then we have two others, right? We have this one here, and that will have a phase of, I call it theta 2. And then we have the vector from the origin up to that point there, and then it has a phase of theta 1. Okay. And this is a, let me see here. If you have this, and this, and this is 60, 30, 90, then this would be, if this is x, this would be 2x, and that would be square root of 3x, right? So x could be any number, real number. Say 1 to square root of 3, when x is equal to 1. So we can find these angles here. In fact, theta 1 is equal to 180 minus the arctangent of 2.6 over 1.5. Right, so theta 1, right? It's got this vertical distance and so that's theta 1, and that's going to be equal to 120. So this theta 1 is equal to 120. Clearly, this is 60 degrees. So this turns out to be, this kind of a triangle, 30, 60, 90, where the x value is like 1.5. And theta 2. Theta 2 is going to be equal to the same kind of thing, 180 minus the arctangent of 2.6 over 0.5. And so that turns out to be 180 minus 79.1, which is 100.9 degrees. So that's theta 2 there. And then these are unspecified theta p and theta z for the compensator. So we apply the angle condition, right? So applying the angle condition, it's the sum of the zero angles which is only 1 and 0 angle, minus the sum of the pole angles, and there are 3 pole angles. Right? So we have theta sub z, theta sub z minus theta p plus theta 1 plus theta 2 is equal to plus or minus 180. Right? You can use whichever gives you the simplest answer. Say I chose 180 minus 180 here, and so we'll call this difference theta z minus theta p. We'll call it phi. The book calls it phi. Okay, and so we have the phi here is going to be equal to, plugging in the values of theta 1 and theta 2, which we know, we'll get this equal to 40.9 degrees. So, okay, because we know theta 1 and theta 2, all we're looking for is this difference, theta z minus theta p. And so this is the positive phase angle that the lead compensator must contribute in order that the root locus pass through that desired closed loop transfer function pole. Okay. So we're not drawing the whole root locus, but we are, finding what this phi here, which is the difference between the numerator and denominator phases of the lead compensator, what that must be in order that the root locus pass through the desired pole. Any questions? Okay, so, and here, again, you can see that there are an infinite number of possible combinations of theta z and theta p to satisfy this. Right? The difference must be that. So the book goes through 2 methods. The second method is what's called pole zero cancellation. So actually, pole zero cancellation, let's see, the pole of the plant is canceled out by the zero of the compensator, right? So in other words, we're going to set A equal to 1, and that's half the problem, right? With the and if A is equal to 1, right, basically this 0 moves on top of that pole, right? And therefore they cancel each other out, right? This theta 2, the theta 2 will be equal to theta z, right? And so theta 2 and theta z cancel out, right? Because theta 2 will be equal to theta z. Okay, so does that sound right?
Yes.
So you set A equal to 1?
Yeah, A would become 1 because the 0 of the compensator will cancel the pole of the plant. Pole zero cancellation.
What's the first method called then we just did? Is that just regular? Did you see the second method is called pole zero cancellation?
Method 2 is pole zero cancellation. Method 1, I don't think you gave a name to
No,
it.
it's just like
Yeah, I'll go through that though. It's just a little bit, yeah. Anyway, when you cancel that pole there with that 0, how many singularities do you have left? 2. You've got that one and that one, right? And you know how to draw the root locus when you have 2 poles, right? come together and breaks away in the middle. Okay? So, if you use pole zero cancellation, you still have the pole at the origin, and you have a pole at minus B. That's the pole of the lead compensator. Okay? And what does the root locus look like, right? It looks like that, right? It breaks in the middle. And in the middle has to be minus 1.5. Minus 1.5. Therefore, what does that have to be? So this has to be minus 3. And B is therefore equal to 3. So that completes the design. Well, it's not totally complete because you have to find the case of C here. Okay, yeah,
How did you come up with -3, Professor?
minus 3.
Yeah, how did you come up with that?
Yeah, because we know that we want the real component to be minus 1.5. Right? That's the desired closed loop, real component of the closed loop transfer function pole. So we know that breakaway has to occur at minus 1.5. And when you have an arrangement like this, breakaway is always going to be in the middle. And if that's the middle, minus 1.5, then the left endpoint has to be minus 3. Yeah, this is minus 1, this is 1.5, that's 1.5. I mean, you could go through and apply the angle condition in order to find this theta p angle here. Well, you know that this angle here is 60 degrees, right? In other words, here's a desired pole, that's a J, 2.6. And the desired pole is, you know that this is 60 degrees, right? And you know that, what the root locus will look like, right? It has to be across, right, that goes through the middle between, the midpoint between these 2 points here. Right? And if this is 60, then that there would have to be 60 as well. Right? So it's 60, 60, 60. So after you find the A and B, which, what is it? A equals 1 and B equals 3, then we can use the magnitude condition. So we use this as the angle condition here. And that point, what we did was we found A and B such that that point, this point right here, passes through the root locus. And so now we can find the gain K sub C that we have to adjust to that value K sub C in order that it does go through that point. So we use the magnitude condition. So the magnitude condition, remember you start out with if you want to, you start out with a characteristic equation, right, which is 1 plus K sub C S plus A over S plus B times 10 over S plus 1. So there's not 10K there anymore because we're not using pure gain type compensation. This is our plant here. This is our plant GP, say, GP of S. And this is our the G sub C of S. So this is equal to 0. That's the characteristic equation, right? And from that, you can find the case of C. The case of C is going to be equal to, and by the way, we can go ahead and cancel out the pole and the 0 there. And it's going to be, this is B equal to 3, so we're going to get minus 10s plus B over S.
No, it's gonna be negative S times S
S
plus
should
B
be on top.
over 10.
That's on
And
top.
then the numerator times S.
Times S?
Yeah.
Oh, yeah. Okay, so we got that. And so we have, putting in the value of, the value, so we have and actually, we could use the alternative form of this, which is the magnitude of that, right? We can use the magnitude of that as well. So it's the magnitude of S times the magnitude of S plus B is equal to 3 over 10. So, you know, if you look at this here, this would be, is 30, this is going to be 3, right? In other words, that's the 30, 60, 90 triangle there, right? And so this is going to be 3. And in fact, this will be 3 as well, right? And this vector right here, this is the S vector. And this vector here, this is the S plus 3 vector. So that has the size of 3, that also has the size of 3. Okay, I mean, this is one way to do it, right? So the size or magnitude that's equal to 9 times 9 over 10. No, sorry, 3 times 3. 3 times 3, 9, is equal to 0.9. So that finishes the design. You've got the case of C, got the A and the B. Now, what we can do is draw the root locus, right? And we already drew the root locus. We basically, when we considered the lead compensator, the root locus is being pulled, attracted by the 0 of the lead compensator. And it will, in fact, go right through that point there, the desired closed loop transform. I can show the MATLAB for that. You'd like to see the MATLAB? Yeah.
You were telling me that there's a very complex conjugate plus J. If you had done that procedure, that minus J, you would have gotten the same value.
Yes, if you use the conjugate, minus 1 by minus J equals 6, you would get exactly the same design.
Million, that would be 999.
It's just that through your image down there, maybe it's complements as an angles instead. So here, let me be sure I'm using the right M file here. I think it's example 2. Here's example 2. Example 2. So execute that. And this also contains, the design, for the method one as well. So let's take a look at, that's the original root locus, right, was pure gain compensation. Right, it just goes together, it breaks away at -1/2. And you can't satisfy the spec. The real component of the spec is -1.5. So it can never, using pure gain compensation, satisfy the specification. This right here is using method one. Let me go to this right. Now, this is method two. Right? And method two, you see it breaks away at -1.5, and then the UK is set to minus roughly 0.9. You see that the roots are -1.5 plus J 2.4. It's supposed to be 2.59. I could adjust that a little bit. It's still 2.4. So it's roughly satisfies the specification. Okay. And it gives a damping ratio. Remember the damping ratio was, we wanted a damping ratio of 0.5. If I adjust it downward,
Yeah, still 2.6. You wanna move it upward, but J is 2.6.
yeah, so there it's closer to 2.6. Damping ratio. But the gain is 0.9. What we had found was 0.9. I might have made a mistake on that. I don't think so. 3. You can determine that gain in different ways. You can just substitute into the expression for K. You can substitute in -1.5 plus or minus J 2.6. Yeah. So, you got 0.9. Yeah. Okay. So the other method is method one. It's not assuming any pole zero cancellation. So let me. And by the way, I just showed briefly what you would get for that case, the other method, and we'll go through it. And by the way, this one here shows the overshoot and the seventh time that we get for the case of pole zero cancellation. So you get about 15% overshoot, and the settling time settles out in about 3 seconds. Actually, you could, if you just right click and do characteristics, then you can see the settling time. And so the settling time is about 2.7 seconds. Time to get within and stay within 0.98, within 2% of the final value is the settling, that corresponds to the settling time. There are other things here that you can take a look at as well. The peak response is there. You see it. It's this 16% overshoot. And so I also just wanted to point out the other case. See, this root locus is the one that we will get using the method one. And I'll go through it. But what you see is that there's no pole zero cancellation. See that the pole at -1 of the plant, and here's the 0, the compensator comes out to be like -2. And so it breaks away, and you have two asymptotes there, right? And you can see that if you adjust the NK, you can get the desired close to the function pole. J 2.6, so it should be up here somewhere, right here. And minus, we want minus 1.5. Right. Plus minus J 2.6. And the gain K is right around 1. Okay. So that's what we want to design now. So I'll move the projector. Is there any questions?
You get the same percent overshoot for this?
Oh, what do we have?
They were both 16%. Is there any benefit to using one of these over the other, or?
Yeah, there is some benefit that I think in terms of the, so this is a step response, by the way, that's what we're looking at, step response. And in terms of the steady state ramp error, this method one here can reduce the steady state ramp error. So that's one advantage of this method one over method two of pole zero cancellation. So I'm going to consider the second method and then the first method.
So you mentioned that that method is better for a reg response. Does that have to do with the asymptotes in function of the response we're analyzing?
Well, they both have asymptotes, right?
Yeah.
In one case, the root locus lies right on the asymptote. The other it approaches the asymptote. I'm really not sure the answer.
Okay.
So, yeah, so this method here, which is method one, I'll just redraw that. In other words, we still need the lead compensator to contribute 40.9 degrees of positive phase in order to get the root locus to pass right through that desired point there. Let me put it here. Okay. Something else. you have the desired pole, which is at minus 1.5 and J 2.6. And so we have the desired pole there. And what we'll do in this method, we'll draw a line, and we'll call this point P here, P. We'll draw a horizontal line, okay, there, and they call this point A here. We draw a vector or a line from the origin to that point there, okay, and then we take a bisector here, okay, to bisect that angle, and so it'll be something like this. I'll draw that dash, right, and then we'll remember phi was equal 40.9 degrees. We're going to make an angle of phi over 2 to the right and left of that. So this point will be minus b, and to the right, to this right here is phi over 2, which is just equal to 20.45 degrees, okay? And that to the right there will be our minus a, okay? Let me remove that minus 1.5 there. This is, point is minus a, okay? And so we remember that this angle here was 60 degrees, right? No, so it was 120 degrees, and therefore this is 60 degrees there. And this also is 60 degrees, which means that this angle in here, all the way from there to there, is 120 degrees, and when you bisect it, it's going to be 60 degrees, right? So this angle in here, it will be 60, and that angle there will be 60. Okay. And knowing this angle and that is 60, this will also be 60. Okay, 60 degrees. And so we can find these other angles in here because we know this angle here is a 20.45. We know this angle is 60, so we can find this angle. This angle is going to be 120, right? 120 there degrees. And so we can find this angle here. It's going to be 180 minus 120 minus 20.45, which is going to give you the 39.55 degrees. Okay. And so you can do the similar thing for this other triangle here. And what we would like to find are the distances here and here. In other words, this distance and that distance. Oh, by the way, this is, remember, this was 60, this was 60 here, and this is 60, and this is 3. This distance, this point here has to be minus 3, right? That point there is minus 3, because it's an equilateral triangle, okay? And then you have these other triangles inside here. You know, we'd like to find this. I call this one B1. I call that B1 in here, and this one A1. If you know, and you do know this is minus 3, then this point here will be minus 3 plus A1. And this point here at minus B will be minus 3 minus B1. Okay, so you can find, what we want to do is apply the, what's it called, law of sines, to determine these A1 and B1. So this technique, you see, takes a little bit more computation. Okay, so I'm not using this. This was, don't need this. And so you can extract these angles out of here, or these triangles out of here. We've got this one here, and so this would be A1, this would be 3, right? That's this one right here. This dashed line has a length of 3. It's 3, 3, 3. Okay, and then this here is 20.45, right? And this angle in here is 99.55. Okay, that's this angle right in here. Okay, and so this angle here is 60. So you can find A1 by using this the law of sines, right? You can say that the sine of 20.45 is to A1 as the sine of 99.95 is to 3, right? 20 is opposite A1, 20.45 is opposite A1, and 99.45 is opposite 3. So we have this, using the law of sines, and so A1 is going to be equal to A1 is going to be equal to solving that 1.06. So that's A1, and therefore the location for the minus A, right, the minus A will be equal to minus 3 plus 1.06, right? Minus 3 plus 1.06. So that's the minus A. Well, and that is going to be equal to minus 1.94. So A itself is 1.94. Okay, 1.94. And then B, you find it, using this other triangle over here. In other words, this one here, where this is 120, this is 39.55, and this is that 20.45. Right? And we want to find that B1. So you apply the law of sines again, you have a sine of 20.45 is to B1 as sine of 39.55 is to 3, because this is 3 here. The 3 there. In other words, this 3 right here. So the two triangles that we're talking about is this one that we're working on presently, and the previous one was this one here. Right? Each of them is got this common side, which is a dashed line. And so you can find the B1. B1 is going to be equal to 1.65. B1. And therefore, the pole location is going to be minus 3 minus that B1. So the minus B is minus 3 minus 1.65. And so that's equal minus 4.65. So the B1 itself is equal to 4.65. And having now the A and B, again, the way to find the case of C is just to use this here. By the way, this we don't have pole zero cancellation now, right? We have two different, we have the A and B here. So the expression for case of C is going to be minus S plus B S plus 1 and divided by 10 S plus A. So if you know A and B, we can substitute in this desired closure transfer function pole, either one, plus or minus J, 2.6, into this, or we can find the case of C as the magnitude of each of these. magnitude of S plus B, magnitude of S plus 1 over 10 times the magnitude of S plus A. Right, so either way, either substitute in or find the magnitude of each of these vectors, if you will, and so that's going to be equal to, is going to be equal to 1.23. So, and then you could take a look at the step response, you could take a look at the ramp response. You could take a look at the ramp response for either of these designs, and the book actually shows the ramp response as well as the step response. So these are two methods, right? And I would want you to be able to apply these two methods here. And like I say, they're really good. You should be aware that there are an infinite number of possible solutions. Remember that you can adjust the values of the A and B, the pole and zero locations of the Lie compensator, such that this positive angle, phase angle contribution that the Lie compensator has to contribute such that it is equal to, in this example, 40.9. Okay. That's a Lie compensation. So we'll review it a little bit next time. By the way, I did post a homework, right? And it has a couple more root locus plots to do, so you get a little bit more practice with that. And then I think there's the lead and possibly lag compensator designs in there as well in that homework. So next time I'll go through the lag compensation. Okay, and I'll review this lead compensation a little bit too. Okay.